One application of loops is finding prime numbers. Number is prime if it has exactly two positive divisors, one in itself. So for example, 2, 3, 5, 7, and 11 are primes, while 4 is not prime because it's 2 times 2, 6 is not prime because it's 2 times 3, and so on. And here's an example where we check whether a number is prime or not. In order to do that, we must check whether it has any divisors from 2 to n minus 1. So to do that, we need a for loop or a while loop like that loops through every single integer from 2 to n minus 1. And we also need to keep track of whether the number is prime or not. So we keep a Boolean variable and initially set it to true. Then if I is a divisor of n, where I is from 2 to n minus 1, then n is not prime. Then we print whether it's prime or not. So if it's prime, print n is prime. And otherwise, print n is not prime. And 137 is prime, but 117 is not prime. Here's an exercise. Modify the code so that if n is not prime, then the program prints the first integer that makes it not prime. So one way to do this is to create an additional variable that keeps track of the integer that makes it not prime, if there is one. Then each time, if I divides n, then we can just set index to be I. Then we break out to ensure index does not get modified again. Then afterward, we can just print it at the end. So n is not prime because index is a divisor of n. And when we run this now, it'll say 117 is not prime because 3 is a divisor of 117. Here's another exercise. Print all positive divisors of n. So for this one, we go from 1 up to n, because this time we want to print all of them. Then if I is a divisor of n, then we print I. Then that prints, in this case, all the divisors of 1,000. Here's a more complicated example. Print all prime numbers up to n. So for this one, we'll need a for loop that goes from 2 all the way up to n, because, well, we need to print all prime numbers up to n. But since we don't want to print the not prime numbers as well, we need to check whether I is prime before printing it. So in order to do that, we'll need the prime number checking algorithm. So Boolean is prime is true. Then for int j equals 2, j is less than I, j++. If I%j is 0, then is prime is false. Basically, this checks whether I is a prime number by checking every single possible divisor from 2 to I minus 1. Then afterward, if is prime, then we print I. And we're done. All the prime numbers less than 100. Here's another exercise. Print the first n prime numbers. So for this one, we'll need to keep track of the number of prime numbers we've had so far. So int num primes equals 0. Then we need an integer that loops from 2 all the way up to when we have n prime numbers. So int I equals 2. Then num primes has to be less than n, because if it's equal to n, then we're done. Then I plus plus. Then afterward, again, we need to check whether I is prime or not. So then we have it there. So this code checks whether I is prime or not. Then if I is prime, then I have to print I and num primes increases. Then we're done. Prints the first 100 prime numbers. The next exercise, print the nth prime number. So for this one, it's very similar to the previous one, except we just want to print the last one. So in order to do this, we'll just modify the code of the previous exercise. So since we only want to print the last one, we need to modify the print statement so that it only prints when the number of primes is n. So then, as soon as the number of primes reaches n, we can do system.out.println I and then get rid of the print statement that always prints. Then this time, it'll print just the 100th prime number in this case. Currently, we have a way to find the nth prime number for an int n. However, what happens when we make n equal to, say, 1 million? Then when we run this, it'll take literally forever because, well, we're running through every integer from 2 all the way up to 1 million. Then for each one, I'm checking from 2 all the way up to that number. So that's essentially up to 1 trillion computations, which is not good. So one way to simplify this is basically, once we're done checking, if a number is not prime, then we just break because there's no purpose in checking any further. And note that this break breaks out of this loop, not the outer loop. In general, if a break is used in a nested loop, then it breaks out of the innermost loop it is in. So it stops executing the prime checking because there's no purpose in continuing the prime checking if we already know the number is not prime. Now, however, this still takes forever because, say, for example, prime numbers, we still have to check every single number from 2 all the way up to I minus 1, which is not good. So one way to solve that is to notice that a number is prime if and only if it doesn't have any divisors from 2 all the way up to the square root of n. So we don't actually need to check all the way up to I. We only need to check up to the square root of it. So j times j is less than or equal to I. And the reason is because divisors of a number come in pairs. So if there's a divisor that's greater than the square root of I, then there must be a divisor that's less than the square root of I. So we only have to check from 2 up to the square root of I. So then that saves a lot of time, and when we run it, after a few seconds, it should give the result. Here's another exercise. Print the first n positive integers that have at most 4 positive divisors. So like, again, previously, we need an int that stores the amount of integers we processed that have at most 4 positive divisors. So int count equals 0. Then for int I equals 1, and then count is less than n, where say n is 100. I plus plus. Then we need to check whether I has at most 4 positive divisors. So in order to do that, we can do int num divisors equals 0. Then for int j equals 1, j is less than or equal to I, j plus plus. If I percent j is 0, so if j divides I, then num divisors plus plus, so that we have a count. Then afterward, we just do if num divisors is less than or equal to 4, then we print I. Then afterward, we have to increase count by 1. And then there's the result down here.